Hello, everyone, and welcome back. I hope you enjoyed your lunch. I can see that some people are still enjoying their lunch, but I also know that we do still have some parallel sessions. So in this room, the plenary room, we will have infrastructure and supporting technology, which is going to be moderated by Philipp Reiss from the Technical University of Munich. And in the delegates room, which you may know by now is on -2, that will be commercial initiatives, dual market case studies, public-private partnerships and market needs part 2, and it's Larry Kujko from ESRIC who will be moderating that. So without further ado from me, I just want to hand straight over and directly, and please welcome to the stage Philipp.
Thank you, Lisa, and welcome everybody to this first afternoon session on infrastructure and supporting technologies. As we're already late, I don't want to lose too much time, and therefore I introduce our first speaker today, who is Paolo Pino. He's Chief Technical Officer at the Volta Space Technologies, and he's going to talk about orbital wireless power infrastructure. The floor is yours.
Hello, everyone. My name is Paolo Pino. And I have been given the very hard job of trying to keep you awake after lunch. I'll do my best. I have a background in materials engineering and space systems engineering, and I am co-founder and CTO at Volta Space Technologies. In this few days, I loved to listen to all your talks about these great solutions and innovations that you're bringing to harness the vast resources of space and of the moon in particular. And we've also discussed how important it is for our community to find ways to make these efforts commercially and financially sustainable. So I'm here today to contribute with what we are offering at Volta Space Technologies to help make this a reality. Speaking about sustainability and commercial viability, those of you who try to pull these businesses off the ground, pun intended, are facing a big issue, which is darkness. As you know very well, the lunar night and the permanently shadowed regions are pretty unforgiving environments. And this forces most of our missions to die in the span of a few days after an investment of tens of millions of dollars. And to add to the criticality of this situation, the solution that we are considering right now to go past this darkness are still affected by limitations themselves. So RTGs are poorly efficient, batteries will die, and surface power plants are cost prohibitive, hardly moved around to explore new sites. So there are limitations here, and it is hard to imagine how any business can thrive if it only has 2 weeks at a time to progress and must every time face massive upfront costs. So the solution to this is to make the power needed to survive the darkness and its extreme conditions more affordable, much more affordable. And this implies reducing the user penalties, i.e. making it cheaper and lighter for you to use that power solution that gets you past the night, slashing the infrastructure costs, i.e. avoiding the large risks and upfront costs associated to landing on the surface, and making it scalable, so making it possible to spread the cost of power over many users, just like utilities do. On the moon, such a utility can look like a satellite, and eventually a constellation of satellites that you might see on the right that was supposed to move, delivering optical energy wirelessly all across the surface of the moon, anywhere and anytime. Now, optical wireless power transfer is not a new thing, but it's never been implemented before or made commercially viable due to 3 main issues. One is the effect of space on high-power lasers. The high-power lasers in space do not survive very long. The stringent pointing requirements, so if you want to beam energy from orbit, you have to be very accurate, very precise, not to waste energy. And receiver technology. You want to be able to convert that energy efficiently and to do so in a manner that does not add a burden or too big of a burden on the shoulders of the user on the surface. So Volta is solving these issues. But before I get to the nitty-gritty, let me show you quickly who we are. This is our team, a part of our team. We are headquartered in Montreal, Canada. We are growing, we're expanding in the US, and we have experience in high-power photonics, laser systems, and photovoltaic technologies, as well as space systems. This is our advisory board that is supporting us into the journey to make power on the moon scalable and affordable for all the users. So back to the previous points, I told you that the effects of space on high-power lasers are pretty problematic to make this viable. We're building a laser that's capable of surviving the harsh environment of space. And you can see here the main progress that we have achieved. The laser that you see on the left is capable of producing 800 watts of optical power. It's an architecture and a platform that can support a power scale-up up to 1.8 kilowatts for this generation. And we're going through the testing campaign to make this space-worthy. So we've already cleared total ionizing radiation dose, single events effects test, and TVAC. And we're planning to go and do shock and vibe testing this year. The second problem associated to that was stringent pointing accuracy requirements. It's extremely hard to be precise. So we're developing a pointing acquisition and tracking system which can overcome these issues. And you can see here what is the improvement. If you don't have any correction in your pointing, you're relying on the most precise additive control system that's available on modern spacecraft. The displacement of the beam sent from 200 kilometers from a lunar orbit on the surface with a pointing error will be of 1.5 meters. We are reducing this by 2 orders of magnitude, bringing that to 3 centimeters. And this allows us to be much more efficient in the energy that we can deliver to the surface. And the third issue was the receiver technology. So how do you get power at the end? What you see in the picture is a first prototype of a receiver that we are developing for our users to install on board their assets. This is very small. The square surface that you see, the active surface within the frame, is just 10 by 10 centimeter large, and the mass is lower than 2 kilograms. So it's conceived to be something that's as easy to integrate as possible, weighs much less than an RTG or in a battery, and can give you all the energy that you need to operate, thrive, or survive during the lunar night or inside a PSR. We are planning, of course, to build new generations, larger. We can adapt to users who have larger power requirements, and we can deliver with this technology tens to hundreds of watts electric. But don't forget about heat. There's going to be waste heat that can be used as well. And we're working on 2 next generation photovoltaic technologies that are going to bring our efficiency up to 50% and more in the next future. So just a quick recap, we're addressing 3 of the main issues that so far have prevented this technology from being viable and usable by users. And I hope I gave you enough proof, but I'm happy to talk about this more. And so let's now look at this in comparison with the state of the art and what are the other solutions available at the moment. When it comes to power distribution, using cables or radio frequency typically is limited to the vicinity of the power source before the hardware required to deliver that energy or receive that energy becomes mass prohibitive. So we're talking about a few kilometers. And so this forces you to stay in the same site. Going elsewhere, it's extremely difficult. Someone is proposing to use lasers, but again, these are not using the right technology to go to orbit, and it's still confined on a surface site. And then, of course, if you're on the moon, you have to deal with a 2.5 kilometers horizon, so you have to be elevated as well, which introduces additional complexity. And when it comes to the onboard mass that you need to get 50 watts, which is something reasonable for a lander to survive the lunar night, for instance, if you wanted to use a battery, that will have to be massive. Same for an RTG, but with Volta, what you need to do is just use this very compact receiver, and we will take care of the rest by delivering that energy from orbit. This is not really meant to be necessarily something that excludes other technology, but this is to say that now there can be a new solution in the diverse energy mix that powers your mission and makes them possible. You can see here well, you know this image very well, right? Everyone is using this, water distribution on the moon, at the South Pole in particular. There are going to be several assets exploring this region, small rovers, small landers, large machines, and you can see roughly how much power they are going to need to survive the night, stay inside those PSRs, or conduct some operations. And in this chart, you can see how much energy a constellation of microsatellites equipped with our technology will be able to deposit on these regions for the benefits of these assets, for them to use. And the model that we are adopting for those assets to enjoy that energy switches from the traditional upfront expense to purchase that equipment, that RTG or battery, to a power-on-demand model where you only pay for the energy that you consume. So we remove the risk and the upfront costs associated to the conventional solution right now. And this energy provided by such a constellation of 30 satellites can provide, can be sufficient for tens of assets in this region to explore and thrive. So back again to the three main things needed to make new missions viable and sustainable and capable of living and thriving longer on the surface. Reducing user penalties is essential. We're trying to do so by reducing the mass that you need and the cost that you have to bear in order to conduct your missions on the surface. Slashing infrastructure cost, we can do that by being in orbit, so we don't have the costs and risks associated to landing infrastructure on the surface of the moon. And it is also necessary to make that scalable. So if you have satellites, we can service multiple customers, spread those costs, and let the user enjoy a much lower price for the watt hour. And we estimate that this can be up to 100x reduction. That is another video that I'm not sure I'm going to be able to animate, but that shows you just a prototype in our lab beaming energy to our receiver, which in turn powers a 3D printer that we were used to print some little gadgets that we gifted to our friends at the Canadian Space Agency. We are progressing and getting some traction among space agencies. NASA and the Canadian Space Agencies have supported us in the early days, but we now have our main customer in the European Space Agency. We're working towards a ground demonstrator happening next year in 2025. So stay tuned, we'll keep you posted on that. And we're actively working with lunar companies, with those of you building payloads and ISRU demonstrators, and things that want to go to the moon and demonstrate stuff in order to make them possible, to reduce the risks, to reduce the cost. So I'm calling you out. Let's talk, let's engage, let's find out how we can make this possible and work together. We can explore how to integrate our small receiver into your assets, and we can understand what's the best solution to move forward. With that, 10 seconds away from the finish, I thank you all, and I look forward to talking to you soon.
Thank you, Paolo. Interesting talk and a visionary concept, for sure. Are there any questions in the audience? There's one here on the left-hand side. The mic, I guess, is coming to you shortly. Yes.
Thank you for the presentation. I don't know if I got it right, but you plan to be on orbit 200 kilometers? Sorry, thank you for the presentation. So, if I got it right, you plan to be on orbit 200 kilometers away from the surface, or what's the distance you are plan to be beaming? And then, what would be the contact time? So, I mean, how often your satellites would go around and provide energy? Thank you.
Thank you for your question. So 200 kilometers is the maximum beaming distance. So that's the distance that we're confident we can deliver energy efficiently from. Now the orbit that we'll be in, we're studying this, but it's going to be a low lunar orbit around 100 kilometers in altitude, and that gives us a visibility window. That gives us a revisit time of about 2 hours and a visibility window of a few minutes. We are studying and building our orbits and designing our orbits so that we can optimize the visibility window, the ability to service the user, but also to maneuver the satellite and be aware of station keeping costs and orbit stability and all these things. But I hope this answers your question.
Yeah, thank you. I mean, what we also heard, some of the orbits are quite unstable. So I mean,
right.
How will you overcome these difficulties as well?
So we are actively studying several orbits to see what are the station keeping requirements associated to those and what kind of maneuvering strategy we will need to adopt. There are solutions, there are orbits which are more stable than others, and we are trying to go into that direction.
Yeah, thank you. It's a big challenge, but yeah, let's hope that you or joining forces, we will overcome this. Because I mean, yeah, for sure, there are also, I know other players also arriving to the industry in this sense. But yeah, thank you.
Thanks.
Is there a second question? Yes, here in the middle.
Hi, Lorenzo Bigizao from ISA. Just a couple of short questions. I hope you didn't mention, I didn't miss it, but did you mention the efficiencies of the laser and then on the opposite end of the receiver? And does the laser also include a lens to deal with the beam diffraction?
Yeah, thank you for your question. Absolutely, the laser also leverage a telescope and pointing system, so optical components that shape the beam, point the beam and make sure that the spot size remains controlled. There was a slide on the efficiency of the receivers that we're building. The first one that we have in the lab is just 16% efficient. This is using commercial off-the-shelf technology though, so we started playing with that to get more confidence and knowledge about packaging techniques and interfaces, thermal control, but the new cell that we're working with is 40% efficient, and that's the second generation only. So we're going towards a third generation of laser power converter, so it's a photovoltaic device that just is optimized to work at the laser wavelength that we need, and that should push the efficiency even higher. So there's it's a considerable progress compared to what's available right now. Thank you.
Okay, thank you very much. Let's thank the speaker again. And our second speaker is Tim Eismann from the Laser Center Hannover in Germany. He's going to talk about the development environment for a regolith melting process for lunar flight demo mission. The floor is yours.
Yes, thank you for the introduction. As Philipp already said, my name is Tim. I'm a research associate at the Laser Center of Hannover, which is an independent non-profit research institute. And on behalf of all my colleagues, I want to talk today about the development of a laser beam melting process of regolith that will be used on a lunar mission and the development environment required for this. This mission is part of the Moonrise project, which the LZH is working on together with the Technical University of Berlin. And here in this video, you can see our vision in the project. We want to develop a laser beam melting process to produce landing pads or paths directly on the lunar surface and from loose regolith. We call that process Mobile Selective Laser Melting, or MSLM for short. And we will deliver a proof of principle for this process on our first lunar mission, which is scheduled for 2026 on a commercial lander. So in April, there will also be a press release about that moon flight and all the information about that. But before we can go to the moon, we have to build the laser first, which are my colleagues currently doing, and we need to develop the process itself, and that is what I want to talk about today. Because we have to develop the process on Earth, we have to simulate the lunar environmental conditions here in our laboratory, which are the regolith, the soil of the moon, the gravity, the vacuum, and also the temperature on the moon. Speaking of the regolith, we use regolith simulant, which is kindly provided to us by the Technical University of Berlin. I think there have also been some colleagues here at the conference, so if you have questions about that, feel free to ask them. Then for the gravity, we are pretty lucky in Hannover because we have the Einstein elevator there, which is an accelerated free-fall tower at the Hannover Institute of Technology. And with that elevator, we can simulate environmental conditions between 0G and 5G for around about 4 seconds. For the vacuum, we use our own laboratory setup that you can see here in this picture. Let's see if this works. Up here, we have our laser source. It has a laser diode in there with a maximum optical power of 200 watts. And this is actually an engineering model of our laser that will be on the moon. The real one for the moon will be a little bit smaller. Below that, we have our vacuum chamber in which we have our powder bed of regolith simulant, which is around about 60 millimeters in diameter and 20 millimeters deep. Connected to our vacuum chamber, we have our pressure gauge. And at the end of the tube, there's our vacuum pump. And with that setup, we can generate a vacuum of around about 10 by the power of -3 millibars in there. And as you might think, with that small setup, we can't really implement much sensors or measuring instruments. That's why we also have a bigger vacuum chamber in which we have much more space to add these instruments. And we will also need that for our temperature simulation setup that you can see here in the schematic. On the bottom left corner, we have our vacuum chamber with a real picture. And in that chamber, we will have our laser, as you can see up here, and a pyrometer connected to that, which will directly look into the melt pool. Below that, we will have our powder container with some thermocouples in there to measure the temperature in the powder bed. And below that, we will have our vacuum contact heater. With that heater, we will generate temperatures between room temperature and around about 150 degrees Celsius. So we can also only monitor the temperatures that are above room temperature. And we will also add some infrared cameras and optical camera to see the behavior of the process. And with all of that combined, we can start developing our process strategy for the moon. And for that, we start with developing the process parameter settings, such as the laser power, which is between 100 and 150 watts, the scanning speed, which lies between 1 and 2 millimeters per second, and the laser spot, which is dependent on the working distance, but normally lies between 0.9 and 1.6 millimeters in diameter. To develop these parameter settings, we use one-dimensional samples, as you can see here on the bottom left. These samples are 30 millimeters long, and we use them for that because they are much easier and faster to produce than the two-dimensional ones that we will have or want to produce on the moon. The two-dimensional ones are 25 by 25 millimeters at the moment, and for these we have to develop a suitable range of hedge distance parameters, so the distance between the different vectors, and we can also work on the scanning strategy. So if the vectors are unidirectional, or if they are meander-like, or even other strategies like remelting, for example. When we have that range of parameters, we can research the influence of the environmental conditions on the landing site on the moon, such as the regolith composition, the temperature, the particle size, and the surface evenness. And with all of that together, we will get our first initial process strategy for the moon, and that will eventually give us our first lunar MSLM sample, which might look like that one here. That one is not perfect. I chose this one on purpose because there are some unmolten particles on there. The geometry is not totally fine and the surface is very rough. And this particular one is also hard to detect on the moon, or would be hard to detect on the moon, because there are these particles on there. If that happens, we can use our knowledge from the process development and our AI tools that we are also developing to optimize our process strategy. And that will give us our optimized lunar MSLM sample, which might look like that one here. That one has a much smoother surface. This surface is also shiny if it's not lighted from behind, so it's better detectable on the moon. And as it's semi-transparent already, you can guess that it's also fully molten. Yeah. But to determine all these parameter settings, we need some analyzing methods. And if we speak of analyzing methods, we differ between during the process methods and after the process methods. During the process, we measure the pressure in the chamber, which you can see on the bottom left diagram. There you can see that the pressure is increasing strongly when we melt the first loose regolith. And then when the laser turns off to jump to the start of the next vector, the pressure decreases and so on. And by the peaks in this graph, you can see how many vectors have been there. So it's 30. And then we also have some videos that we capture, and we gather pyrometer data. As you can see here in these videos, they're working perfect. On the top, you can see the first melting of the raw regolith simulant, and on the bottom you can see the remelting of the already solidified sample. By the way, these temperatures are not real. And in these videos, we can see how the melt pool is behaving. We can see this, how the size is developing. We can see the pores moving. And we can also see, especially in the top one, how there are some unmolten particles sprayed on the melt, which leads to this bad detectability. Then in the future, we will also be able to measure the temperature of the sample and of the powder bed, and we will add a mass spectrometer to the setup to figure out the elements that are in that gases that are evaporating. After the process, we take the samples out of the vacuum chamber, we weigh them, we measure the dimensions, and we analyze the surface roughness. And after that, we will produce some cross-sections of these samples, of which we determine the porosity via some image processing scripts, as you can see here in this little schematic. So we have the cross-section on the top, then we remove the background, and then we count the pores. And this particular sample has a porosity of 15%. After that, we also do some hardness testing, which is our only mechanical value. So these samples have a hardness like typical glass. And in the future, we also want to add some bending and fracture testing, which might especially important for the landing pads, for example. I think on Monday we had a presentation about that, how fixed such landing pads should be. And we will also add some XRD measurements in the future. And with all of these methods combined, we will get a lot of data and information about the process. And I think there's also even more information in the literature, but that's where we kind of get a problem, because I know there are many researchers out here, and some of them are probably here in the auditorium, and everybody is doing it a little bit different. Some are using different simulants, some are using sieved or ground powders, some are using substrates or even atmosphere. And all of these are optimizations to what we will find on the moon. And for that, these results are not really comparable. And this is where I want to make my call for collaboration. We should work together, figure out how we can quantify these differences and how we can compare our results to, get to the moon together. And with that, I want to sum up my presentation. I've told you that we are able to simulate the vacuum, the gravity, and the regolith to some extent. We will soon be able to partially simulate the temperature on the moon. We are currently able to produce two-dimensional semi-transparent samples, and we have multiple analyzing methods as I've shown you. And that's it from me. Thank you very much for your attention, and I'm here for questions.
Great talk. Thank you very much, Tim. Are there questions from the audience? Yes, in the second row.
Difficult to remain silent when you have a burning question until the microphone arrives. How many square meters can you do on a day with a laser a suitable rover can carry? Can you estimate that?
Not totally, but as I've said, we are moving with 1 millimeter per second at the moment. To produce a sample, as you have seen, the two-dimensional ones, we need like around about 4 minutes. So you can add them up how long it will take. But we also have to think of that the laser needs to cool down, so you can't use them all days. And we are at the moment working on giving the proof of principle. And after that, I think we need to have some heavy machinery to scale that one up.
So am I right that within the Moonrise project you have some 3 kilograms as a solid-state laser?
It's a diode laser, yeah, and it's currently 3 kilograms, as you have seen that one there, and the one for the moon mission will be 2 kilograms.
And you know how to cool that in vacuum?
I'm sure my colleagues know how to do that, and they are working on that.
Okay, good. Thank you. Good luck.
Thank you.
Are there any other questions from the audience? Yes?
First of all, I want to thank you for the presentation, and I have a quick question. Why did you use a laser for the melting and not a solar concentrator?
The easiest answer would be because we had a laser center, but yeah, because a laser is probably, I think, easier to control and smaller than a big lens for solar light combining, as I hope I got that right from you. And yeah, we choose a laser because compared to other options, because we don't need any tools and it only needs energy. And we could get this energy from the solar and use the laser.
Okay, thank you.
Maybe I can have another short question. Yeah, very interesting. Out of the landing site properties that you presented on your one slide that influence the process, which are the most influential ones, like temperature, grain size distribution, mineralogy? Is there something that sticks out and that is really hard to control?
Yeah, first of all, they don't differ that much. As long as we're not totally lasering on a big rock, then I think the composition has the most impact. But what has the most impact for us while finding the influence of these landing site conditions is how we can replicate them in our laboratory. And there we have some other values that have a lot of influence.
I'm sure you will learn a lot out of this first demo mission.
Yeah, I hope so.
Let's thank the speaker again. Thank you very much.
Thank you.
And we need to move on. The next speaker is Roberto Torre of the European Space Agency. And he's going to talk about low binder content bricks, state-of-the-art progress towards a sustainable construction on the moon.
Yes, thank you for the introduction. And good afternoon, everyone. My name is Roberto. I'm a research fellow at the European Space Agency, European Astronaut Center based in Cologne. I have today the pleasure to talk with you about the advancements we made towards a sustainable construction on the moon regarding using low binder content bricks. This is a concept that we already introduced last year together. The idea of this presentation is to show you the advancements we made, where we are, and what will be the next steps. So to give you a little bit of introduction and a framework, I'm a part of Spaceship EAC team, which is based, of course, at EAC. It's a group of young researchers. We have been working in the last year as a team with different kind of technologies that might help to turn the regolith into a functional material for manufacturing and construction purposes, but using both binders or not. More recently, we started to think about how we can go from lab scale, so from manufacturing small items, small samples, towards surface construction or better civil engineering on the moon, which is quite a big advancement. because as you can imagine, there is quite a significant amount of material that we need to handle, process on the moon in order to build a surface construction. So sometimes when we talk about materials for constructing something, we think about the physical and mechanical properties, which of course are important, but we also need to think always about the efficiency of the process in terms of time and energy, the scalability to those bigger dimensions. If consumables are used, we need to try to minimize them as soon as possible, as much as possible. We also need to think about the environmental constraints, both for the material itself and also for the process that we want to develop. We are trying to keep all these things together by taking advantage of some of existing or available processes or solutions which limit the complexity of the idea we have and enable a quick transition to the payload. So what we want to do is to develop a regolith-based low binder content material. So it's a composite material because a binder is involved. The binder is a thermoplastic material. We wanted since the beginning to have a process that is as simple as possible, and also we wanted to have the quantity of the binder as low as possible. And we found out that a solution to have this is to standardize the shape of the parts that we want to build. That is building what on Earth we call bricks or tiles. We choose to follow this approach because we know that bricks work on Earth. We have been using them since the Egyptians. And also there are some similar concepts to what you will see in the next few slides, like polymeric cements or compressed earth bricks that work perfectly. Also, when we use bricks, we can have a production facilities which is way smaller than the infrastructure we want to build. And also it's very easy to automatize the production, the assembly, and maybe also the repairing processes that might be needed. Of course, the question is how low can we go with the organic phase, so with the binder. So let's see this in the slides. Our process is considering at the moment EAC-1A, which is the regolith simulant we use at European Astronaut Center, and Peak as the thermoplastic binder. Actually, you will see in this first slide that at the beginning we were using also PLA or polyethylene. The idea was simply to understand the process a little bit more, and then to switch to the real polymer we wanted to use. So the process is really simple. We start from the regolith and binder in dry, powdery form. We mix them together. We compact the powders into a mold that will give the part the shape that we want to achieve. And then we cure the part at the polymer's melting temperature. Some of the results you see here have been just published on Discover Applied Sciences, so I really recommend you to have a look to the paper. As a first step of the process, we wanted to understand it. So we wanted to understand its feasibility. We wanted to understand which were the mechanical properties we could achieve, and also which kind of geometrical details we could have. You see from the picture that we managed to go as low as 5% in binder content, which means 95% of regolith. And from the ESA logo you can see on the right, imagine that it's 6 centimeters in diameter. So you can realize that we can really have fine details, sharp angles, and thin surfaces. The graph you see on the bottom shows you the trend of the compression strength of some of these bricks with PLA against the binder weight percentage. And you can see that by playing with it and also by playing with the compaction pressure, we can cover a wide range of compression strengths, which perfectly overlap to the properties that we need on Earth for industrial floor bricks, building bricks, etc. So it seemed quite promising. So we decided to go a little bit more into the details, and we did an extensive mechanical characterization campaign based on design of experiment approach. We wanted to see which was the influence of all the process parameters that we were using, and we found out that the binder weight percentage, of course, the compaction pressure, and the regolith grain size were influencing the mechanical properties, and there was a way to have really a set of optimized mechanical properties. We did everything considering the compression strength and the flexural strength as how to put parameters. As a second phase, we finally switched to PEEK, which is the final polymer that we would like to use. And we saw that all the experience we gained using PLA could be transferred. So that was like a good choice. And we narrowed our focus into the specific process values that we saw were actually playing a role. You see here the relationship between the bending strength and the peak weight percentage for a different set of compaction pressure. To give you a reference, between 5 and 10 megapascal is what we would expect on Earth for a common cement. So we can really cover this, this purpose. So once we understood that the mechanical properties were quite good, we wanted to go into the details of the geometric shapes that we could achieve. So we wanted to demonstrate that it was really possible to have bricks with a specific shape that they could be assembled together. The picture you see in the middle shows you the mold that we developed. It's only missing the lid to make it visible. And on the right, you can see the bricks. This is one of them. So if you are interested, you can have a look later. As you can see, it's like very solid. So it's a big piece of rock. And the animation on the right shows you the assembly of a wall. Of course, it's like a very simple animation. It's very a simple geometry as well. It's not a geometrical or topological interlocking, but it's a proof of concept of the possibility that this technology gives us. We also, of course, we want to understand where, in which field we can use this kind of material. So there are lots of tests that have been planned. One of these is what you see here on the picture. So we want to see if we can use this material to shield from radiations. So actually, we are going to build several walls. Then we are going to stack them into a sequence up to 50 centimeters in depth. And then we will see how this material behaves against high energy ion beams. We plan to do this in roughly 20 days, starting from today. So we will have some results very soon. Okay, so this was like the proof of concept of a wall, which is a vertical surface. Of course, if we look at our habitats, we cannot live without horizontal surfaces. So we also try to see if we can work on some designs for horizontal surfaces. This is quite a recent development. The design of the tile you see here was developed in collaboration with a group of students of the Politecnico di Torino and Politecnico di Milano. I have it over here as well, and I really recommend you to come closer to this tile and to see the geometrical details, how fine they are. We plan in the middle of this year to do a plume surface interaction test to see how they behave. The idea is that we want to understand where we can use them. So maybe they could work as a landing pad, maybe as the structure below the landing pad itself, or maybe just as a simple pavement or a road. We will figure it out this soon. In parallel, we also want to demonstrate that this technology is so simple that we can quickly turn it into a payload concept. So the prototype you see here on the pictures, of course, it's not space graded yet. It's just the first machine that we are trying to build to demonstrate that this process can be automated. So you see there is a regolith binder intake on top, then there is a mold with a thermal system in the middle, and also a compaction system that is capable of keeping the pressure applied while the brick is being cured. We are building it at the moment, and we plan to test it at ESC in the Luna facility as soon as it will be ready. And then from there, we will see how to go further and to make it space graded. Another approach that we have been considering recently has been the sensorization of these structural elements. So we thought that if we really want to meet the lunar harsh conditions, but also the high safety standards which are typical of crewed expedition, we might need some of our structures or some areas of our structures to be actively monitored by a network of sensors. So we thought that Optical fibers could be a good solution. You might be familiar with the concept, but you can turn an optical fiber into a sensor by creating a Bragg grating on it, and then you can measure the strain. So we developed a process to integrate these fibers into the brick. You see the picture on the right. The fiber is somehow visible, but you can imagine it's transparent and very thin. And the fiber is inside of the brick. It was cured within the brick, so it's integrated with it. And our technology is really suitable for doing this because the temperature are not that high, so the coating of the fiber can survive, and also the compaction pressures that we apply, they are not that high. Processes that need higher compaction pressure wouldn't be suitable for this solution because of the high shear strengths that will be developed across the fiber. So we can say that so far, we managed to integrate them into our structural elements, and we started to calibrate them. We started also to do some thermal cycles to see how they behave and which kind of measures we can get. And yeah, that was my last slide. I hope I gave you a nice overview of the status of our project. Of course, I'm very happy to take questions. Thank you.
Thank you, Roberto. Thank you, Roberto. Are there questions from the audience? Matthias again.
So thank you very much. I have two hardware questions. So your polymer binder triggers the question, how does it behave at low and high temperatures and the cycling? I admit I do not know any data for the comparative technique if you use epoxy. So how does it do if you cycle it through 300 Kelvin? And how many fibers, Bragg fibers, do you have to implement and break before one works?
Yes. Okay, so regarding the first question, so far the only thermal cycles we tested was a limited one. It was going between plus 60 and minus 60 Celsius degree. We will increase the cycle in the next future. So I don't have a proper answer.
So it works plus minus 60, or is it becoming brittle
yes.
already?
No, it works, yes. What I can tell you is that the peak itself would work at low temperatures. It might become a bit fragile when very low temperatures are considered, but the behavior of the composite material is still something that we have to see. Regarding the parallel with the epoxy, we chose to go to thermoplastics because we found out that since we can use them in a powdery form and a dry form, the process is a bit more simple. We don't need high pressure to squeeze the epoxy resin across the powdery material, and also thermoplastics are better resistant to UV radiations than the epoxies. Regarding the fibers integrations, the integration was something we did in the labs at a lab scale. So quite a few fibers broke during the phase. The thing is, you need to be really careful in handling them while you put them inside of the mold. But after that, the process is quite safe. So after we understood how to avoid them to break outside of the mold, we managed to have at least 3 or 4 bricks in a row with the fiber that was intact.
Question answered. So there was another question online. I think that is at least partially answered by Roberto. If not, let me know in the chat. There's another question.
I have one question.
You have one?
Yeah,
sure. Go ahead.
So basically, I'm not sure if it was clear. What did you use for heating the thermoplastic binders? So I wanted some insights on that, and also, are you planning to apply any, aerogel layers for thermal insulation or anything else for radiation shielding? Because I think there was no stats on the thermal insulation and radiation shielding properties of your current material.
Yes, so regarding the heating phase, so far we used a common oven. What we will do in the next few months will be to try the process in vacuum to see how it works with heating the brick in vacuum and curing it in vacuum. And the thermal properties were not studied so far, I'm sorry. It's something we will do now that we know that we can integrate the fibers, because we can measure the temperature from the inside through the thermal strain. So we'll do it in the real next future.
Thank you. And anything for the radiation part?
I mean, we know that adding the polymer might improve a little bit the radiation shielding properties. PEEK is somehow safe in this respect. It has been studied by CERN, and it's quite insensitive to radiation, so it should withstand. Thank you. Thank you very much.
No more questions? Okay, I have a quick question. Maybe you can still answer that, because we have a bit of time left over. Do you already think about recycling the thermoplastics at the end of the lifetime of these bricks?
Yes, so we didn't try this with our bricks, but in principle we know that this material can be recycled, because in one of our previous research we did at TAC, we were combining again a thermoplastic with regolith to produce filaments for 3D printing, and then we tried to recycle these filaments, and we saw that the mechanical properties of the recycled material did not differ that much to the properties the material had before recycling. So in principle we think that we can recycle the bricks that might break. So yeah.
Okay. Excellent. Thank you.
Thank you.
Okay, thanks again.
Thank you.
And we are moving on to the next speaker, who is Jonas Walther from the ETH in Zürich in Switzerland. And he is going to talk about autonomous construction of a boulder blast shield on the Shackleton-Hansen connecting ridge.
Yeah, thank you very much. My name is, as you said, Jonas Walther. I'm working at the Venturi lab, and what I'm showing you today is something which I did previously at the ETH Zurich. So I would like to start with a short motivation. As you all know, the Artemis program is planning, in contrast to the Apollo program, to establish a long-term stay on the lunar surface. And having a base on the moon brings some challenges with it. You can see an animation of the Apollo 17 relaunch on the lunar surface, and as you can see, a lot of dust and debris is ejected during this launch. And this is a serious hazard for everything which is close by, and imagine you would not want to stand next to this or have your house built next to this without any further protection. So it makes sense to, for example, build a blast shield around the landing pads, and yeah. A further challenge is that transportation to the moon is quite expensive, and therefore it makes sense to use in situ resources, and I guess this is why we all are here. The ETH Zurich has developed a robot called HEAP, which stands for Hydraulic Excavator for an Autonomous Purpose. It is capable of autonomously building dry stone walls. You can see this in the video on the right. And note that there's no human inside the excavator. It really does it automatically. It's like a robot. So dry stone walls are basically walls where you put just stones on top of each other without any mortar in between. And it has the advantage that you can use local material. You don't need to process or pre-process the material, and this makes it very energy efficient. So in this presentation, I would like to talk about whether this method would be applicable to build a boulder blast shield on the moon. I will first talk about the required amount of boulders which we would need for this, then about how many boulders are available on the lunar surface, followed by the path to collect the boulders, and finally also energy and time. Yeah, so for the blast shield, I consider a blast shield which is around a landing pad of 50-meter radius. So the rocket would need to be capable of doing a pinpoint landing. This, however, is not unrealistic as we construct this landing pad and blast shield before any rocket is landing there, so we could install the required infrastructure for a pinpoint landing. The blast shield will furthermore be assumed to have a height of about 3.3 meters, which gives a reasonable shielding angle. Furthermore, the landing pad is assumed to be rather in a corner of the lunar base then in the middle of it, and with this we only need a quarter ring segment of a blast shield, so we don't need shielding in all directions, but only in a quarter of the directions. And the resulting amount of boulders which we then need is about 250 cubic meters. So given this required amount of boulders, it makes sense to have a look at how many boulders are actually available on the moon. And for this, we looked at images of the LRO, so of the narrow-angle camera. You can see a very small snippet of such an image on the top, and on the bottom you then can see how we mapped boulders inside them. The boulders are basically the bright features with a long shadow behind them, and they can be distinguished from craters because the order of bright and dark pixels is exactly opposite. We mapped boulders in the whole connecting ridge Artemis candidate region, which is very close by to the actual lunar South Pole. You can see in the visualization on the left where it is located. And on the right, you then can see again this region with black dots in it, and those black dots are the mapped boulders. So the images of the LRO have a very high resolution, but this resolution is still not good enough to see very small boulders. And this is what I'm going to talk about next. So in the diagram here, you see on the x-axis the size of the boulders, and then on the y-axis the cumulative number of boulders of this size or larger. The bluish small dots then are the mapped boulders, so basically the data. And down to a size of about 2 meters, we can expect that we should see almost all boulders inside the images, and below we cannot be sure whether we see all. And the boulders which we would like to use for construction, however, are of a size of about 0.5 meter to 1.5 meter. And this is visualized in the diagram as the bluish range. So the boulders we would like to use are smaller than what we can reliably see in the images. And to solve this issue, we used size frequency distribution laws and fitted those laws with the large boulders which we mapped, so with those data points, and extrapolated to the number of smaller boulders. Size frequency distribution laws are quite commonly used in planetary geology, for example, also to assess how hazardous landing sites or potential landing sites for rovers are. And usually exponential laws are used or power laws. And which ones are correct for the moon depends a little bit on the actual age of the specific region. You can see fits of those two laws as those curves in the diagram, so the red and the orange curve. As you can see, the red curve expects less smaller boulders, and because of that, we chose this one for the upcoming slides because it's more conservative. So to get an idea of how long the distance would be, we would need to travel to collect those boulders. We implemented a path planning pipeline, and you can see the result of this in the animation. You can see that the robot needs to move back and forth quite a lot of times because it has a limited payload capacity. The path planning pipeline, furthermore, also takes into account the slope constraints of the vehicle and keeps it out of permanently shadowed regions because they are extremely cold and also scientifically interesting, and we do not want to drive through them. The overall distance then is about 780 kilometers. This now sounds like quite a lot, but when we compare it to how far the distance was, which we traveled with the LRV in Apollo 17, with only 3 EVAs, this was almost 36 kilometers. And so this number then does not seem anymore that large. Next, I would like to talk about the energy consumption of this construction method and compare it to other construction methods. So our method would require about 2.8 megawatt hours, and this includes the energy for collection and placing of the boulders. Other construction methods which are proposed by literature are, for example, cast regolith or microwave heating, where the basic idea is to heat up regolith until it melts or sinters. And as you can see, our method would require about 2 to 3 orders of magnitudes less energy. You can also see this visualized on the right with the blue rectangles, which compare how the solar array area would compare. So next I'm going to talk about the required time for construction and the required energy, and how it depends on the payload capacity of the vehicle which collects the boulders. In the previous slides, I was assuming that the payload capacity is quite large, so 10 cubic meters. This is about the payload capacity of normal European dump trucks. And yeah, you can see in the diagram on the x-axis the payload capacity, and on the y-axis in blue the required time, which is about 60 Earth days operation time for the reference value. And in red you can see the required energy. And as you can see, we can reduce the payload capacity by quite a lot, and the time and the energy won't increase very much until some point where it really starts to increase. So what we basically see in conclusion is that the appropriate vehicle size will be a little bit larger than what current rovers have, but it could be much smaller than what terrestrial trucks have. Yeah, so in summary, we saw that this construction method of using dry stone, or of constructing dry stone walls autonomously does not need material processing, which makes it very energy efficient. This is also the main advantage of this construction method. Furthermore, we saw that there's some uncertainty on the actual available amount of boulders on the moon, and the results which I showed you, however, are conservative in this respective. And also when we have more landers landing at the lunar South Pole, we get more images which have high resolution, and then this uncertainty will get smaller. Yeah, and last but not least, we also saw that the vehicle can be smaller than that of than terrestrial dump trucks. Yeah, so thank you very much for your attention, and then I would be open for questions.
Thank you very much. Do we have questions in the audience? Not yet, so I'm going ahead and ask a question myself. But there is one, two, at least one.
I was just wondering if you did any like geometric studies of the wall itself, like a trapezoidal shaped wall versus the direct vertical stacking that you mentioned, and if that has any efficiency in resisting those plume interactions.
The assumed shape was actually trapezoidal, and for this we looked at how dry stone walls are usually built on Earth, and there it is suggested to have a little bit of trapezoidal form factor.
Okay. Is there another question? No. I was wondering what orders of magnitude in terms of sizes of landers do you anticipate to land in this landing site?
Yeah.
Are we talking about Starship or smaller landers?
Yeah, the values which I used for the forces which are on the wall are actually for Starship, and they are actually probably rather an overestimation of it. So with full thrust, yeah, so probably the walls could also be much thinner if a smaller lander would be there.
I see. Okay. Thank you. If there's no question, thank you very much for your talk. And the next speaker is Niels Koek from Yokogawa, and he will talk or present a water analysis module with direct measurement. The floor is yours.
Right. Thank you. Yeah, good afternoon, everybody. So I'm from Yokogawa, but I'm not the only one here. So we really now present you a consortium of companies, mainly from Japan. It's a commercial companies, but we also collaborate with the universities in Japan. So, yeah, maybe first question would be why are we going to the moon as commercial companies? This is handy. For us, it's two main reasons. It's to build the energy plant by utilizing the water on the moon and to make a moon society and to allow for further space exploration. And the other is to make the connection between Earth, Moon and the cislunar society. So for the first reason, the energy plant, we believe that we can extract the hydrogen and oxygen from the water on the moon. And of course, that is essential for deep space exploration. And to do that, we need to build a facility like an energy plant. So these energy plants will contribute to the infrastructure, the lifeline and human activities on the moon. For the second reason, we believe that as the commercial companies, we can bring existing technologies on Earth to the moon, and also the other way around. So specific technologies developed for the moon for specific usage on Earth. So one example would be projects to grow vegetables on the moon. But yeah, we should also maybe look at growing vegetables in harsh environments like the desert on Earth. Is it working? I hope somebody can help me out here. Yeah, there it goes. So this is a mock-up picture of what we are currently developing. And this module shows you that we can measure how much water is in the regolith. So it basically consists of three elements. A drilling to really excavate the regolith, a vaporizer to vaporize the gas in the regolith, and finally a laser analyzer to identify the molecules in the gas. And on the right-hand side, you currently see the size that we have developed to date, and to date is since 2021. So it's approximately 60 centimeters in height, and then 30 depth and 30 in width, about 10 kilograms, and it can drill about 50 centimeters in the surface of the moon. Now this is an explanation of how the analysis works. So we use already existing technology from, in that case, Yokogawa. It's called a tunable laser diode. So basically we have a sender and receiver, and depending on the pressure and heat of the gas, we can tune the laser into the water molecules and measure the absorption. So on the bottom you see a spike, and there is where the measurement of the water is being made. This is the bench test, where you see the different elements shown in the mock-up module. So you will see the tunable laser diode. You see the vaporizer in the middle and the measuring cell. And of course, we collect the data via PC. And I'll show you a small video of the test that we made, where we can really inject the water and measure the absorption and the pressure, and also the content of the specific sample. should work. Yeah, here we go. So here you see the vaporizer. And underneath you will see the drill. The example here is that the drill excavates the regolith from the surface of the moon. Having the regolith, it will then be heated and transported into the vaporizer. Once in the vaporizer, we can start to measure the water content. And then once we have the gas, we use the bench test, as you can see, and explained earlier, to really measure the water content in the sample. Now, please be aware that this left-hand side picture, for you the right-hand side, typically this is on Earth very big dimensions. It's about the sender and receiver needs to be a couple of meters at least to have an accurate measurement, and also the sender and receiver in size are about 1 meter in diameter. So now we, as a company and a consortium of companies, are downsizing this model for users in space, and currently we are at 60 centimeters in total width. Our plan for the lunar spring water is to start with, together with iSpace, to mount it on a lander and do a proof of concept in 2027. And then next would be to extend that to a rover. We also will use the proof of concept to see if we can drill deeper on the surface of the moon. And as you can see here, we plan for a commercial model in 2030 with the idea to create a water map of the moon surface. Now, this is currently the team. So the kind of orange color and blue color, that is the consortium of companies working on this lunar spring water model. But you can also see on the right top end, the gray area, is that we are very open and welcoming any other commercial or academic institute to collaborate with us to make sure we can make this energy management on the moon. The timeline for our future business, so currently we are still in the development phase. We did start with the prototyping and the technical feasibility. So currently we are moving into detailed design and create the engineering module. And then in 2026 we really want to make sure that we have the proof of concept to go to the business phase, which is then bring it actually to the moon and start collecting the data. Basically, that was it from my side, and I would like to repeat that this is a presentation not only Yokogawa, but also Shioda, iSpace, and the Tokyo University. And again, we would welcome any company that would be interested in working with us on this. Thank you.
Thank you very much. There's one question, Jerry. Oh yeah, great.
I cannot see it.
I was just told we have a lack of personnel to bring the microphone, so we might have to wait a little bit longer.
Jerry Sanders, NASA. So a couple of things. One is you talked about the lower measurement capability of the tunable diode laser. Is there an upper range in which you saturate that capability? The other is, how do you measure the mass of the sample that you're going to heat in the vaporizer to give you an accurate water content capability? And then just as a comment, if you weren't aware, NASA funded JPL to create an instrument that could measure water content down to the ppm level.
Okay.
To understand water in oxygen before it would get liquefied, and it's extremely small, so you may want to look into that, called LIRA, right? L-I-R-A.
Okay. Well, thank you for that. Yeah, we're currently still in the bench test phase, so we are now using a predefined kind of mass and kind of sample, because we are in the phase of basically tuning down the laser technology first. And then the second step would be to create basically the answers to your questions.
Okay, because you have to be very careful in terms of the saturation level, as well as if you don't have an accurate measurement of the mass of the sample going in, then your understanding of the actual content goes down tremendously.
Yeah, correct.
Thanks for the nice talk. One question is concerning isotopes. Have you tested the instrument as well with respect to identifying isotopes?
No, we're really focusing on the water molecules.
Should be accessible as well with TLS, I think. So that's maybe to add a little bit of a science seasoning to the whole story. Could be advantages.
Okay, thank you.
Maybe to expand on that, you showed what other species you will be able to measure with the future models. Can you explain a bit more what you target there?
Well, basically what you can do is, of course, influence the frequency of the laser. And depending on the frequency and heat and pressure, you can measure any kind of molecules that you want by absorption of this laser beam. But the current focus is because typically now the laser beam needs a kind of a big length to measure accurate. Our first mission is to have this shortened and specifically for water molecules. So maybe in the future it can be.
And what are the temperatures that you heat the sample up to? So would you potentially release a lot of other species volatiles?
I don't know that on top of my head.
Okay, right. Any other questions? I don't see any in the chat. No? Okay, so thank you very much. And already we are at nearly at the end with the last speaker in this session, Mr. Mohamed Makthoum from Spartan Space, and he will tell us something about the development of a dusty thermal vacuum chamber. Please.
Thank you, everybody. So my name is Mohamed Makthoum. I'm from Spartan Space. It's a new space startup based in Marseille, France. I'm here to present the development of the dusty thermal vacuum chamber that will be installed right here in Luxembourg in Bellevue. This is the presentation content, so I just give you why we need the DTVC chamber and what is the objective of the current project and the timeline and where we are in the project. So I think this is a bit old presentation, but that's fine. Why do we need the dusty thermal vacuum chamber? We all know that it is similar to the thermal vacuum chamber. You need to validate and qualify your space equipments. In addition to that, DTVC also has two unique problems. One is that it it simulates the planetary surface, that is, you need to deal with regolith. We know from the Apollo missions that the Apollo surface equipments that were left behind, they failed because of the lunar day and night cycle, that the regolith simulants fell on top of the radiators and they caused the failure. And second, we also know that in the Mars rover scenarios where the Mars simulants, they deposited on top of the solar panels and then they got failure. And the second unique problem of the dusty thermal vacuum chamber is thermal vacuum chamber does not like dust inside them. So we need to look from that side as well. We need to work on that side. Now, second, the dusty thermal vacuum chambers can be classified into 4 broad categories. Scenario 4 is basically that you can test the entire payload inside or the spacecraft inside. And scenario 3, which is the interesting part for us, which is where you test subsystem level. In this case, the planetary surface subsystems can be the size of can be very small because satellites can be several meters high and spacious. But if you look at all the planetary surface subsystems or the system itself, the rovers and everything, they are much smaller when compared to geosatellites or James Webb Telescope or something like that. And scenario 1 and 2, these are very small chambers. Our friend earlier, he presented one such chambers that they used in laser Zentrum, Tim, he presented that earlier. So where you can do smaller experiments, but scenario 3 is needed when you want to test as a whole, as either a rover or a drive time operations or radiators or something like that. So for this project, there is 3 partners. As I said, we are a startup based in Marseille. The core team has extensive experience in developing such chambers. Our main business is development of human exploration technologies for extreme environments. So, but we lack infrastructures. That's why we partnered with Mana Electric and Aux Life Support System. Aux is the largest hyperbaric and hyperbaric chamber producer in Europe. They have developed over thousands of chambers. And we have also partnered with Mana Electric. Most of you here might know them. They are the experts in developing solar panels from ISRO, both in Earth and in the Moon. And they are also building a scenario 2 chambers in their facility. Now, for our chambers, so we designed our chambers to go up to 10 to the power of -9 millibar. Without the regolith, with regolith, we are targeting -6 millibar. This is the ECSS standard as well, recommending that the range we need to test. So the chamber, if I might say, the nose to tail, it's 5.3 meters, and then toe to head, it's like 3.5 meters tall. But again, this is the external one, so it's quite big. So you can imagine the inside volume is 2.9 meters by 2.36 meters in diameter. So that fits most lunar surface rovers inside as a whole inside. So the thermal range, we can go from -180 degree to +160 degree. We are using liquid nitrogen to go to the cold vacuum level, and then GN, gaseous nitrogen, to go to the thermal high level over here. And the hatch here is designed to allow modularity in the sense that if we want to, in the future, install a solar simulators, that the hatch can be easily rotated or moved, and so to enable such expansions possible. The chamber also has a camera system looking from outside in order to monitor your progresses. And it also has several flanges for future expansions possibility, like volatile zones and extra other types. So the first problem with designing the dusty thermal vacuum chamber is the dust, the regolith simulants. We need to protect first the hatch because you need to protect the seal if you want to guarantee a good vacuum level. So that is why the chamber is designed in a little bit different than the other thermal vacuum chambers you might see where the hatches move usually in front or side and stands. So here it is designed on a double hinge system where the hatch will open and then go to the sideways. So it is protected from the dust direct contact. Of course, you cannot avoid 100%, but there is some limit. From the pump, rotary pumps, and then the cryo pumps, we don't have to worry about them, but the turbo pumps, they really don't like dust because the turbo blades can damage as well as the bearing. For that, we have installed 2 turbo pumps with buffers in front of them. It reduces a little bit of their pumping speed, but it protects their pump, and also a purge valves to protect against the regolith simulants in the bearing side. In addition to that, since our chamber has one other unique property, which is dust simulations or dust sprinkling from the top of the chambers. So here we need to be aware about the boiling effect of the regolith simulants. Matthias Perel and other material specialists might know here that in the beginning of the pumping process, all the trapped gases will escape from the test bed, creating agitations in the regolith, so you might have premature deposition of the simulants, so we need to avoid that. So in order to do that, so we designed our dust dispenser and then the bottom tray. So it serves two processes. The bottom part where you have a test bed, it holds the payload as well as acts as a simulant bed where you can do tests such as laser sintering, solar sintering, excavation, and these kind of tests. And then at the top, we have 6 sets of dust dispenser, which are basically 700 bins, which are filled with 10 centimeters of regolith simulants, where they, like a pepper mill, they deposits the simulants on top of your test bed. This way, you can test your mechanisms, radiators, solar panels, and so on. So this is one of a kinds in the Europe. Normally, we have dust chambers, but not such like these kind of chambers. So we have to de-risk them. So to do that, we are currently working on the breadboard for the dust dispenser. So the dust dispenser, it has 2 stages of operations. So the first stage, and both stage operates more or less the same way. The reason why we went with 2 stages is to avoid this boiling effect. Even if you have some boiling effect and if you have premature sprinkling, so these ones comes to the second stage and then stays there till the motor starts the operations. That's the main purpose. So the breadboard is to validate and de-risk the entire mechanism. And second is also the mesh selections. So what is the simulant level we need? We know that the energy needed to elevate simulants above 50 microns is not possible. So regolith simulants, we know it can go up to several micron bigger, but that is not really interesting for us. What is very interesting for us is the macro and nanoparticles, which is what we want to simulate, because during the lunar day, these are the ones that are floating up, and during the lunar night, these are the ones that are depositing. The second effect you will have in lunar surface is also the scooping effect, where from a rover, or we might have seen from videos from Apollo, where you will have a lot of regoliths getting out of the wheels and then depositing on nearby equipments. For these kind of things, we can simply run the experiment longer and get it thick up to 5 to 10 centimeters. It will depend on the mesh that we are going to select. So the timeline-wise, we are right now in the de-risking as well as the procurement of the chamber itself, these phases. We will start assembling the end of this year with our factory acceptance tests and site acceptance tests in the H1 of next year, and hopefully the chamber will be operational in the Q3 or Q4 of next year. And that is it from my side.
Great talk, thank you very much. Questions? Do we have any? Yes, oh yeah, sorry, I'm blinded by the light. Go ahead. Let me see, we have a microphone here. Thank you.
So I'm looking forward to your chamber being operational, and this is not only a funny suggestion, but we should have maybe a symposium of all funny physics effects that happen if you handle large amounts of regolith simulants and rule out that people mistake it for something we should expect for the moon. So how mobile will the chamber be? So it will be in the premises of Catherine's here, and is it accessible for a more general public?
Well, from the stakeholder side, it is accessible for general public, but it's a stationary platform. It's located in List here in Bellevue. It cannot be moved. It's 6 tons.
So how would it rate in comparison to the specs of the Korean machine?
The Korean one, that is much larger than this one, where they also have a large test bed, but you don't have this dust dispenser over there. And that's the main difference between there and here. And also it's in Europe. Yeah.
Sorry.
My name is Christian Dalsgaard. I'm from Denmark. A lot of this has actually been operating in Aarhus at the Aarhus University. Unfortunately, very much in the academic world, and that's maybe new. But I wonder, some of the concerns that I have is how much volume would there be on doing tests in this scale, And have you considered any dual use or exploitation of dusty vacuum chamber from the business perspective?
That's a good question. So there is 2 points. Normally, the scenario 1, scenario 2 chambers, they exist throughout Europe. A lot of universities and research institutes, they have them. It's only when it comes to when you want to test the whole subsystem, this is where the problem that is coming over here. So the usable volume, as I said in the previous one, it's 2.3 meter diameter by 2.9, so it's quite big. With the dust dispenser, it is reduced a little bit. It's 2 meter by 2 meter, approximately. Now, for the dual use case, one is the space, and the second one is a little bit limited at the stage, but you can also see that is why we also have partners like Mana, where they have these kind of dual use capacity, where they use sand to create solar panels. So these are the things that you can test. So if you are working with any materials test or dust related to particle science, those are the experiments we can test in this ones.
Okay, Robert.
Thanks for the talk. You mentioned 10 to the minus 6 with, let's say, regular simulant load.
Yes.
Do you have any limitations in terms of the amount of regolith you can accommodate in terms to achieve this level of vacuum?
At the moment, we don't. So in our calculations, we took all the worst case scenarios. So the chamber can have like almost half a ton inside. So that is the calculations that we made. There is 2 points in the regolith outgassing rate that you can calculate. The one that you can calculate is the trapped moisture and all those things. That is easily calculatable. Plus also you can run the pumps a little bit longer to activate for this. This is why the chamber has 2 cryo pumps and 2 turbo pumps in order to compensate. Now for the chemical outgassing of a factor of that one, that we really don't know. That we will know when we actually test it, like what will be the difference. But we don't think it will be a majority factor because the outgassing from the moisture, it accounts for 95 to 95% of the rates. So it shouldn't be very significant.
Okay, thanks a lot. Maybe one bonus question. Yeah. You have a cold plate in there, obviously, I would assume, right?
The thermal shrouds?
Yes.
Yes.
And I mean, only shrouds or as well a cold plate, because that would enable you eventually